Thank you again for this day and for who you are and for the ministry of Mike Adams. We thank you, Father, for, well, his service to God. Thank you that you've gifted him. And I thank you for that. And I pray for your blessing on his wife, who struggles so much. And Lord, how she's feeling now, I just pray you'd give her some kind of lift. She's been at it a long time, and she's remained faithful. And I pray you'd minister a double measure of grace. I don't know how to add a single measure, but you can do something to it so it's multiplied to bless and enrich her. I pray you do that, Father, in Jesus' name. Amen. His wife, I've never had a migraine. I've had a headache. Had a bad one once, but that's it. But his wife had migraine since she was 12. And she was healed in 2017. And for a year and a half, she lived without one.
Wow.
And then they came back, which is even worse. Man. So she's been, to say she's been faithful, is an understatement. She's married to Mike, so. So, I don't know, I don't know if I should ask you to take notes for this one. Some of you may have seen this, but I think it's really funny. Well, it's insightful.
I used to believe everything I'd see on the news, but that's before I discovered a brain.
A brain is meant for everyday use. Those living with moderate to severe stupidity have seen immediate improvement in common sense with a brain.
I thought the government had my best interest at heart, and then a friend told me about a brain.
Talk to your doctor about what news sources you obey. A brain may also lower your desire to take life-altering advice from celebrities.
Getting lectured about my carbon footprint from people with 3 private jets used to make sense. But thanks to a brain, now I can think for myself every day. When my disregard for third-grade biology began to flare up, I knew it was time for a brain.
Do not try a brain if you're allergic to a brain. Common side effects may include accountability, discernment, homeschooling your kids, a better understanding of economics, awareness of the stupidity of socialism, and diarrhea.
Still a no-brainer is choosing a brain. Ask your doctor if a brain is right for you.
For more information, visit tryabrain.com.
Should I say that?
And buildings. Because if we're
This guy's really great, but we don't have time to listen to him. He's just, to say he's chill with this, he is. He's just level and straight and thoughtful and he's not angry. He got canceled from his job because he didn't even do exactly what they said he did, but anyway, it's a really good bit, but you're not watching right now. Yeah, we'll get that. So, people do some funny things, brain things. Anyway, so I passed out all those little pieces of paper for you, and I'm going to start out with this one. I think that's the first one that's on there, scientific method. That's what we're going to talk about. And actually, I've got a couple of things on that. So, in one of them, you will see this in color at the end of this, and it doesn't have anything for you to fill out. It just kind of reiterates what this goes through. Hypothesis building, that's what we're doing. So, scientific method is a process for experimentation that's used to explore observations and answer questions. So it's just a method. It's not like they always have to be in this step, this placement. They don't always have to be exactly this way, but this is a general method for approaching using experimentation to explore what your observations are. Okay, the scientific method used for research for searching cause and effect relationships in nature. In other words, an experiment is designed so that changes to one item cause something else to vary in a predictable way. And I think there's an example. Let me see, make sure this is, otherwise. Yeah, okay, good, I'll get there. So you start with a problem or a question. You develop something that can be solved through experimentation. Then, this is hypothesis building. Then you make observations, you do research, and then you formulate hypothesis. It's an educated guess about how things work. So if I do this, then this will happen, or I would expect this to happen. If I did this, then this, I will expect this certain result to happen. So you predict a possible answer for the problem. So, an example from agricultural economics. So, if soil temperatures rise, then plant growth will increase. Say you could posit that. So, if the soil is warmer, plants will grow faster. So, you must state your hypothesis in a way that can be measured. So, and that's what you're doing with the formulation of a hypothesis. And then you're going to test your hypothesis by doing an experiment. So you would create, if you were going to do this, I know I studied at Virginia Tech, and I had friends that were in agronomy that did this very thing. They created several plots, the same soil, the same location, same, if it was going to rain, it would rain on all of them equally, with the same plants at the same stage of growth, and set it up so you can heat the various soil plots to different temperatures and measure the growth of the plants over a given time. So some of the stuff it gets pretty complex. This is how are you going to heat the soil so it's evenly heated, so every plant in your little plot is heated the same, and the soil, you keep measuring the temperature, so you keep a plot of each one so you can compare them and say, okay, we heated this up, and then that stayed this hot for so long, whatever. And then you keep one plot as a control group, so you would just have normal soil temperature. It wouldn't have any heating in it. So it's very simple. So your experiment then tests whether your hypothesis is true or false. So you're saying, okay, the hotter it is, they will grow more, at least initially. So it's important for the first experiment to be a fair test. You conduct a fair test, making sure that you change only one factor at a time, while other conditions are going to stay the same. You repeat your experiment several times to make sure the first results weren't just an accident, and then you collect and analyze the results and see if they support your hypothesis. So that's pretty simple, but that's about how you'd approach it. So then you include a statement that accepts or rejects hypothesis, like this does show, or probably if you covered a wide range of temperatures, you would probably find that when it was heated to a certain degree, that it didn't increase growth, but it retarded it. And possibly heating to a couple degrees would exacerbate growth. But heating it too hot, you could fry the seed, or you could cause the plants to wilt. So you have a range. You'd be working within a range each time. Let me see. Okay, so this is not it's not really a digression. Thomas Edison. It was interesting to read about him. So, how many failed attempts did Thomas Edison make at the light bulb? So if you Google this, there are lots of numbers, not just a few, about this. So Edison, the number of attempts he took to invent the light bulb, from 500 to 10,000. The truth is that he didn't invent the first light bulb, but he did invent the first incandescent light that would last and was practical. So there were lights out there, but they didn't last, they weren't practical. He invented the first one that was practical and lasted, and it took 2 years and many failed attempts before he would discover success. A reporter once asked Edison, how many times are you going to fail at creating the light bulb? He replied, I haven't failed. I've simply discovered another way not to invent the light bulb. So, some additional quotes. That's Thomas Edison in a more relaxed position outside of one of his labs. Genius is 1% inspiration and 99% perspiration. Accordingly, a genius is often merely a talented person who has done all of his or her homework. So, opportunity is missed by most people because it is dressed in overalls and looks like work. That's why class, although this isn't a prayer class, that's why most people don't know how to get in touch with God. Because tarrying before Him and investing the time and effort it takes to get in touch with God, people aren't willing to do. It's easier to go work and do something. So, I never did anything worth doing entirely by accident. Almost none of my inventions were derived in that manner. They were achieved by having trained myself to be analytical and to endure and tolerate hard work. Those are quotes supposedly by Thomas Edison. Makes sense. And this is a little sign that said, this room is equipped with Edison electric light. Do not attempt to light it with a match. Simply turn the key on the wall by the door. It looks like this. It had on, and then it had off. So you could turn that to tell whether the light was on or off. You would probably notice it if the light glowed. But if it wasn't glowing, you could tell anyway that something was made. But anyway, the use of electricity for lighting is in no way harmful to health, nor does it affect the soundness of sleep. That may not be true for everybody, but that's what it was. There's a picture of a more professional picture of Thomas Edison. So this was in a room where they hadn't had electric lights, and so they were installing them, and they had to have some description about what to do. So in here, just for your visualization, light bulbs with carbon filament were first demonstrated by Edison, October 1879. Carbon filament bulbs, the first electric light bulbs, became available commercially that same year. So that's a picture, it's kind of hard to see, but that's a picture of basically the first one, and this is what it functionally looked like. So it is. Put electricity through this would glow, and this filament would glow, and then you'd have light. So that was what it looked like. Now, okay. So that was one. Now you're through that little deal. Yes?
Could we go back to number 4? Sorry.
Number 4. Number 4 is right here.
Thank you. Yeah.
Okay, now, this is, you don't have, you have this little piece here, you already have this, so how you're going to get there, I'll just show you what I did to do this. So hypothesis building. So this is an illustration of a jalopy race back in the 30s, 40s. So note this jalopy, they're going around the corner really quickly, and 2 wheels have come off the ground. Now, this is just one example of those 2 wheels coming off the ground, but that's an example of that car needs some kind of stabilization, so all the tires are on the ground. with one of them off the ground, one of the ones that, these are all rear-wheel drive, so with part of the drive off the ground, you're not gonna be able to go like you want to go. So it would be good if they could create something that would keep this down, and that was a problem with the rear ends of cars going high speed to lose traction. So that's what happened with that one, going around the corner, lost traction. The problem was stated, formulation of a problem, and someone hypothesized that perhaps the air flowing around the automobile could be used to keep the rear end down. So you could do something to the automobile to keep it down. Models were designed and put in air tunnels where smoke was used to track the way the air currents flowed over the vehicle. So they were experimenting with repeated observation. And so air comes over here and down here. So the suggestion was, well, I won't suggest before we get there. After examining the airflow configuration, a design for rear spoiler was hypothesized. So if you could do something to capture this air that's going over the car already, it would perhaps tend to keep the rear end lower. I mean, this is simulated. So how you'd capture this, that's what they were working on, how to figure out getting this air. And the air may not necessarily just flow exactly like that, but they looked and see how it did, and then they designed something. So design was created for a model, experiments were conducted, repeated testing, and when the results of these tests were collected and analyzed, consistently giving successful results, the design was enlarged and attached to a vehicle. So they did a lot of stuff before they stuck something on the back. More experiments were run testing the design. Eventually rear spoiler became part of motor racing development and history. So there's a spoiler on the back of this car. I mean, some of them you can adjust. I mean, you have the ability to adjust what this is depending on how you're running. I mean, they're really sophisticated now, but that was the process. They wanted something to keep the rear end down, so they got something that keeps the rear end down, which is what they wanted to do. So you get better movement out of your vehicle to accomplish what you want to on that one. So that's a rear spoiler. That's just that. I thought, well, I like cars, and so I thought that would be a reasonable explanation for using cars. So that's that one. So that's the one that you have out that's in color. And now I want to do this. This is Dr. Stephen Meyer. This is 5 minutes and 30 seconds.
Can you believe in God and science at the same time? So-called new atheists like Richard Dawkins and scientific materialists like Neil deGrasse Tyson certainly don't think so. To them, religion gets in the way of science. In their view, more science leads to less God. This is not a new position. It was first expressed over 100 years ago by English physician John Draper in a book titled History of the Conflict Between Religion and Science. Draper, who was deeply influenced by Darwin's then new theory of evolution, regarded organized religion as a direct and existential threat to the advancement of science. As he put it, religion and science are absolutely incompatible. They cannot exist together. Mankind must make its choice. It cannot have both. So are science and religion inevitably in conflict?
Have they always been? Well, not exactly. In fact, the giants who established modern science, astronomer Johannes Kepler, chemist Robert Boyle, physicist Sir Isaac Newton, and others, were deeply religious men. They didn't see any conflict between science and religion. On the contrary, they thought that by doing science, they were discovering God's design and revealing it to mankind. Indeed, it's no exaggeration to say that the Judeo-Christian religious tradition led directly to modern science. To back up this claim, Cambridge University historian of science, Joseph Needham, posed a famous "why there, why then" question. Why there in Europe? Why then in the 16th and 17th centuries? Why didn't modern science start somewhere else before then? After all, the Egyptians erected pyramids. The Chinese invented the compass, block printing, and gunpowder. Romans built marvelous roads and aqueducts. The Greeks had great philosophers. Yet none of these cultures developed the systematic methods for investigating nature that arose in Western Europe during the 16th and 17th centuries. This realization led Needham and other historians of science, such as Ian Barber and Herbert Butterfield, to look for some other X factor to explain why the scientific revolution occurred where and when it did. Here's the conclusion they reached. Only the Judeo-Christian West had the necessary intellectual presuppositions to enable the rise of science. So what were those presuppositions? We can identify three. All find their origin in the Judeo-Christian idea of a creator God who fashioned an ordered universe. First, the founders of modern science assumed the intelligibility of nature, that nature had been designed by the mind of a rational God, the same God who made the rational minds of human beings. Thus, these men assumed that if they used their minds to carefully study nature, they could understand the order and design that God had placed in the world. Second, they assumed an underlying order in nature. This was best expressed by the philosopher Alfred North Whitehead, who argued there can be no living science unless there is a widespread instinctive conviction in the order of nature, a conviction he attributed to belief in the rationality of God. This idea led to the unprecedented use of mathematics to describe the orderly processes at work in the world. And it inspired the invention of better instruments, such as telescopes and microscopes, to see that order. And third, these founders of modern science presupposed the contingency of nature. This simply means that God had many choices about how to make an orderly world. Just as there are many ways to design a clock, there were many ways that God could have designed the universe. To discover how he did, scientists could not merely deduce the order of nature by assuming what seemed most logical to them, that is, merely using reason alone to draw conclusions, as the Greek philosophers had tried to do. For example, the Greeks thought that since the most perfect form of motion was a circle, they assumed that the planets must have circular orbits, something that Kepler later refuted by careful observation. Indeed, because of their theological convictions, the new scientists realized that they would have to observe, test, and measure in order to understand God's design. To these men, nature was like a book, a form of divine communication, intelligible to human investigation. For this reason, they also developed the concept of the laws of nature, implying God's governance over the natural order. Science was a way to decipher that order. The idea that science and religion are in conflict is a popular belief today, but the history of science shows otherwise. All of us, laymen and scientists alike, owe a great debt to the Judeo-Christian tradition. Without that tradition, we'd be living in a much more primitive world, morally and scientifically. I'm Stephen Meyer, historian and philosopher of science at the Discovery Institute for Prager University. Thank you for watching the...
So this is obviously this is a 5-minute, 30-second piece. And there's a lot. When he talks about this, I probably haven't, I've watched it, but he goes into a lot more detail about this historically, how it fit. Why we have in Western Europe this explosion of real, a systematic method for investigating nature. That's what it was. And because there was a foundation there. Not everybody was a Christian, but you have Judeo-Christian, you have Jews, you had people believing in Christ, but believing in God, who was systematic in his creation. There was a system to it, or it could appear, so they began to look at that, not assuming because of their own thinking, but they were using observation, testing, and measuring to establish what was going on in nature as they were observing it. So, anyway, I thought that was interesting. I was working on creating a handout for you, but I didn't do it. So, now, I think I will go to, let me see, we've done the first two. We're going to go to scientific theory, this handout, and so this is part of this is from your book, or a lot of this is taken from your textbook. I don't know if I stayed in here, but one of the notes I had was they had some things written. Oh yeah, I do. We'll get there. Okay. So does anybody any comments or anything about the bid, or what do you? There are so many. If we have time for them. But showing one in class, we just don't have enough time to show all. I like, any of you, do you all know about the idea of irreducible complexity? No? Yes? Okay, some of you do. It's where something created has so many components, and if it was missing one, it wouldn't work. And so the idea of undirected processes like evolution doesn't have a goal. It's just survival of the fittest. Those that are equipped to survive, and so having useless information doesn't last long. You could have a mutation that gives you information, but if it doesn't better facilitate your existence, it's gonna be lost. I mean, you're not gonna survive. Plus, the energy to create it is a waste if it's not doing anything. So if you need a bunch of different parts to be there all together at the same time to work, the idea of evolution doing that is, well, it just doesn't happen. So evolutionists are trying to figure out ways of structuring or stating that there are pieces made, and they're probably working on other things, but it's possible for them to disengage from their original purpose and connect with other items that are there for other purposes, and pretty soon suddenly you've got this thing that works. That does what it's supposed to do, like a bacteria flagellum, that's the common one that they talk about, or Strididis, whatever. But a little bacteria has this little flagellum that makes it move through matter and get food source. So it needs this little thing to process through. Well, I found an experimentation with it over the couple of years when it doesn't have to move to get food. They're giving it food to see how it operates. Well, pretty soon it loses the use of this. It doesn't need it anymore. It doesn't need that little tail to spin on a little motor. It's pretty ingenious, that one thing. And there are other issues that the blood clotting is just an incredible mechanism that the body does, but to think that, well, it do this little piece of it, and then later on do this piece, it's got to work together. It's got to be a complex thing. Anyway, so there are they're figuring, evolutionists are trying to answer the question, how can you get something developed from unguided processes and mutation that ends up developing something that wasn't already developed. And it's a far reach. It's a real far reach. I mean, I haven't studied that myself, so I'm a little bit on a leap, but it's interesting to me. Anyway, so all science is based on the assumption, this is from our textbook, that the natural world behaves in a consistent and predictable manner that is comprehensible through careful systematic study. The present is the key to the past. It's uniformitarianism. The theory that changes in the Earth's crust during geological history have resulted from the action of continuous and uniform processes. Now, the overall goal of science is to discover the underlying patterns in nature. And then to use that to make predictions about what should be expected given certain facts or circumstances. That's what modeling does. Modeling takes certain factors and it brings them together and say, okay, if this and this and this, then we would predict. That's why they're worth predicting weather. But they've got so many factors to look at to predict weather. It's we'll get there in a couple months from here, or a month and a half from here, talking about weather. But what they're trying to predict is really complex. I mean, the air we breathe, I mean, in eastern Kentucky, you don't know what the weather's gonna be. I mean, with all the mountains, with the river valleys, I mean, it's just, there's so many, you find out every day what it's gonna be. They speculate what it's gonna be. They can speculate, and they have models, many models. And I talked about that before. Anyway. So, to determine what is occurring in the natural world, scientists collect scientific facts through observation and measurement using the 5 senses, often with enhancement, like this young woman is looking through a microscope. That's enhancing her ability to see. And that's pretty primitive at this point, but nonetheless, that's what you're using, their senses. Once facts have been gathered and principles have been formulated to describe a natural phenomenon, investigators try to explain how or why things happen the way they do. They try to explain it. They often do this by constructing a tentative or untested explanation, which is called a scientific hypothesis or model, which is an informed guess that tries to explain how or why an event occurs. So it's an informed guess. What is an informed guess? Well, it's a hypothesis. You're looking to see whether that hypothesis does some accurate prediction. So after one scientific hypothesis are advanced, once they are advanced, this is a similar, where I'm using more or less the book to talk about what I've just spoken of with Edison and the spoiler in a car. The same process. Scientists think about what will occur to be observed if a hypothesis is correct and devise ways and methods to test the accuracy of predictions drawn from the hypothesis. Testing usually involves making observations, developing models, and performing experiments. The model is a picture that shows a concept, event, or object that cannot be observed completely in its natural state. The internal structure of the solid Earth is an example. The interior of the Earth has been evaluated by all kinds of indirect means, because we've never gone down. We haven't gotten through the crust. So we haven't, nobody's drilled through the crust. So we don't know what's under there. But they use indirect means to try to get there. They look at, seismic. They actually, in detonating underground explosions, they know it's precisely how deep, when, and where, and they can measure how the waves, and there are different waves that travel through the Earth. They travel at different speeds through different media. You're gonna find out about that next session, or the next session we go through after we're through this. And you'll find that they go through, so they can measure these things. So they know when they're speeding up or slowing down. And so they can tell that's why they have discovered that there is as I said earlier, a couple, maybe last week, the week before, there's a body of media that can hold water. Well, they've done that through seismic testing. And they know a lot more about seismic waves now than they did 5 years ago. I mean, continually studying them, how these things operate, and they can tell what kind of material they go through. So, we don't know for sure. We have a pretty good idea of what there is and its composition. How it functions, however, is still speculative, hypothetical stage that we don't know for sure. We haven't been down there. So this little guy, I don't know, when I was growing up, that was a big thing. Stick a knife in there. If your mama was in the other room, she'd know you did something. She might not know what it was, but she would hear you. And I use that in my prayer class to say, when that little boy gets connected, when he sticks that knife in that socket and that thing is hot, he's going to yelp. And his mom is going to hear him. Well, most people pray and they never get close to that. They don't get any connection. They just believe. It's a faith thing. Well, talking with God doesn't have to be just, I gotta believe that he hears me. We can know. So when a hypothesis has survived intense scrutiny, and when competing hypotheses have been eliminated, a hypothesis may be elevated to the status of a theory. A scientific theory is a well-tested and widely accepted. Now this inclusion, because evolution cannot be tested. Creation cannot be tested. We cannot test them. So, how do they get around that to call it an evolutionary theory? Well, they skip this part and they do this. Now, the video when I first turned on this machine and I had the Berlinski was talking. Great man. I don't know that he's godly, but he thinks really well. And he said consensus, the idea of consensus making something right, is neither scientific nor reasonable. I mean, that would mean the more people that believe something makes it righter than something that the most people don't believe. Well, that's bogus. That's not scientific. Science doesn't work on consensus. Not at all. But this widely accepted deal, that's why I put it in blue, because the scientific community agreeing, the scientific community has fought new revelation. Have you ever read about Lister, the guy that Listerine was named after, who started to thought that washing his hands between operations would not spread germs? He was ridiculed. The idea that people would operate. They'd operate one person after another. They'd never clean up. They'd never wash their hands. They'd just keep going from one to another. Well, the success rate was a lot lower than it is when they started washing their hands. Just the idea of not intensely, just washing their hands, washing the gunk and whatever they got off of the previous operation, washing and cleaning, and then going into clean. Well, he was ridiculed. Just that one, how small is that? That's not, well, it is scientific in a way. He had done some study. I should look. I write those things down. Well, I don't remember. It was mentioned to me before class about an extra credit. Does anybody know about extra credit? Anybody? Anybody? Nobody? Okay, well there is. There is extra credit on this. Not this, but I have it. And but I keep forgetting to It's not, it has to do with Noah. And so today is Monday. If I can locate it and tweak it, well, I know where it is, but I can tweak it so it plugs into where we are and isn't too laborious. I'll send it out. If you want to do it, you can do it. It's not required. I'll note it as extra credit so you can see it. Everybody when I send an email, or when I send email through Populi, everybody gets it, I assume. Okay. So, anyway, widely accepted consensus doesn't have anything to do with real science. Anyway, theories should not only fit the data used to formulate them, but must have predictive power. Theories are, therefore, only accepted provisionally. Even a theory is only acceptable provisionally. This is what the book says. It is always possible that a theory has withstood previous testing, may eventually be disproved. Now, this quote right here is true. But that was from the 2000 Earth Science text. Your current one doesn't say this anymore. They have jettisoned this particular, and for being an evolutionary oriented book, for good reason, because it doesn't match. So there's Albert Einstein, for just, I don't know, because I wanted a picture. Yeah. Science is ongoing. The data gathered from previous observations and experiments plus new observations become accumulated data used to formulate hypotheses and leads to further observation and experimentation. Similar conclusions from different areas of study also allow scientists to arrive at a theory. When I was doing my master's thesis, so what I was doing was evaluating choices farm family people in farms were making in the state of Virginia. And I didn't really want to do that, but God had other plans in mind, so I ended up working to minister to my major professor rather than to do what I wanted to do. I wanted to get involved with international trade and agricultural development overseas. That was my interest. They put me working with this other professor, and it's a long story. It's a great story, but God put me where I needed to be to minister to this professor. And she taught me how to write well. Part of that was just what I'm going to tell you. So, my thesis, I spent 2 weeks writing one paragraph. So if you're a perfectionist in here, I had it down. 2 weeks, I got one paragraph. I worked on that paragraph. It felt good. It sounded good. It was a great paragraph. And I turned that in for her, and she looked at that, and she said, "In 2 weeks, Jim, this is all you've done?" And she took her red pen, and she destroyed that paragraph. She didn't destroy it just to destroy it, but she said, "What you say here is not germane to what you're studying. It might be something somebody else can do in their research. So this goes in an addendum. So you put it at the end of your thesis. It's a good idea, but it doesn't have anything to do with what you're doing here. This has nothing to do with anything. You can erase this." And she carved that thing up. And I was left, I don't know if I had a sentence left. And that led me, and I'll just tell you this, because this is my class. So I realized that I don't procrastinate purposely, but I just do other things when I think of them. So if I have a job, then I would think of something I needed to do quickly, so I'd go do it. And then I'd come back, and then I'd do something else. Well, I didn't get a lot of things. I didn't get the main thing done. Well, I realized that issue. And my friend prayed for me, and I knew God heard his prayer. I knew it. It was on Sunday night that God would help me to prioritize, to not keep allowing myself to be distracted. So, Monday, I did the same thing I'd always done. Tuesday, I did the same thing again. Wednesday, I did the same thing again. Thursday, I did the same thing again, and I went to pick up my wife in my car, and I was early, and so I pulled over to the side of the road and just wept. I said, Lord, I can't do this. I'm intelligent enough to know what it is. I just can't change myself. I cannot change myself. And I wept. Picked up my wife the next day, got up in the morning, she went off to work, I went, sat down at the computer, Cat sat on my lap, so I'm ready. And then I think of something I can do. I start to get up, and God said, no. I said, well, just take a minute. I'll just do this quick, and I'll be right back here. He said, no. 2 hours. I sat arguing with God. I got nothing done. I mean, the cat was asleep, but I couldn't get anything. I was so frustrated. And I don't know, it may sound weird to you, but I could not get up from that seat. I could have forced up, but God wanted me to stay there. And finally, I was so angry, I just started, and I typed 2 pages, and it got it done. I got 2 pages done. Well, it wasn't great, but there was enough in those 2 pages for me to work with. And that broke it. And I still have to restrain myself from doing something that I could just take a minute to do when I need to be focusing on something else. I still have to exercise my own, but God helped me. From that was a turning point. But I had to come to the place where I realized I could not do it. Now, my friend prayed for me, and I knew God heard his prayer. And I just thought that God would answer it. But he had to take me to a place where I knew I couldn't do it. And I just couldn't do it. And then God helped me. But it was painful. I tell you, I didn't say bad words to God, but I was really angry. But after that, I could just do it. And I can do it now. I mean, it's years later, and I can still, God really helped me. But I needed help that was bigger than I was. So, the first step of the scientific method is making observations, and certain assumptions are laid down that eventually direct conclusions. It's not so much a question about the evidence, the data, but how you view the evidence. You've heard that before. If you don't get that right on the test, I should count double off. I don't know how, well, I could do that. I had a professor who did that. I got to be able to figure out how to teach math. So, but don't miss this. It's not so much a question about the evidence or the data, it's how you view it. It's about the assumptions you make going into the study that determine the outcome. You go in thinking, okay, God created the earth, 6 literal days, then I'm going to look for something that would have that context. That's some of the reasons why people say they're looking for where the Garden of Eden is, and they're doing this and that, and they're looking for the rivers that are named similarly to what they were in the Bible. Well, you had a worldwide flood between the time God created that thing. You had water covering everything. And if water covers everything, and then water recedes, it erodes, and it changes the whole landscape. It wouldn't be anything like you saw it. It wouldn't be anything, if you were there and had seen it, it wouldn't be anything like you'd seen if you were on the boat with Noah. I mean, he was there. He was there in that area. And so when he got off, I mean, the land looked entirely different than it did when he got on that old boat. So anyway, the most beautiful system of sun, planet, comets could only proceed from the counsel and dominion of an intelligent and powerful being. That's Isaac Newton. Now, I don't know that that's Isaac Newton, but that's what he said. Which body of assumptions best fits the evidence we have? Best explains what we observe and the natural processes we know to be true. Why do you find seashells on the top of high mountains? Well, a flood doesn't prove it, but it just says, wow, that's a reasonable explanation. If there was a worldwide flood, you would expect to find marine life on the top of mountains. If there was a worldwide flood, it makes you scratch your head. So we need to be very careful about making assumptions about the actions of the past by observing actions in the present. The assumptions can extend backward or forward, some sequence or rate occurring over an observed period of time, does not factor in the likelihood of differing environmental conditions, catastrophic events, speeding up or slowing down natural processes. And one can easily err in reasoning from effect back to its cause. And I said before, I said in the lecture the last time we met or the time before that, this same thing, it doesn't mean that you can't do it, that it's bogus totally, but it's not so strong. The evidence is not strong. So scientists can, it is noted and verified, miscalculate, misunderstand, and misapply information. They can do that. All these guys here can do that. All scientists out there. Anybody wearing a white coat you see, they are human, and they can misunderstand. And how they do is based on what assumptions they make. So, and with 5 minutes to go, I think I'll just let you go. I have a